to give a presentation about our recent investigations on quantitative micro and nanoplastic analysis of environmental samples. I would like to apologize if I'm not looking directly into my camera because I have a second screen, but that makes life much easier. And so let's start. So first of all, a lot of things are already said, so I don't want to summarize everything on this slide. I hope you can see my mouse. Yes, that is good. And we all are recognizing that microplastics and nanoplastics are ubiquitous and even found in remote areas. A lot of things are already said, so I here just want to point out that microplastics and nanoplastics are by far the most challenging, complex and heterogeneous analytes because they are heterogeneous on one side and they are particulates. So it's not as easy as any solvable analyte to be analyzed. There are a lot of urgently asked questions that are also placed this morning or this today. And a lot of things have to be decided by reliable analytical data, and at least also potential legislative implications are asked. Therefore, the characterization is very important, and long time it has been practiced by optical methods and even directly picking particles from samples. But by now, this is not enough for reliable identification and quantification of microplastics. And a lot of methods have been developed over the recent years. Very common were particle-based methods that have been already developed, and by now also mass-based methods from complex as a complex technique are more and more in focus due to their high potential in microplastic analysis. And a very nice recent review have summarized all the new approaches that are available by now. A lot of things are already done, so I can quick go through this picture. We have heard a lot of FTIR already, and it's a non-destructive technique working with electromagnetic interactions of polymers for specific identification. And you receive polymer type answers and particle counts, size and shapes of your samples. And also these automatic analysis approaches have been shown already. So mass-based methods, in contrast, are destructive methods. That is not as good. So in a succession, they are always the last analytical tools. And the polymer is decomposed with temperature and under the exclusion of oxygen. We get a pyrogram after time resolving with a gas chromatograph, and we get mass spectra after detection with mass spectrometry methods. We get answers about the polymer type, and now we get bulk masses of respective polymers that enable a lot of approaches. The methods, and that is already pointed out, are highly complementary and both necessary because numbers tell a lot about toxicological relevances and give information included in these studies, and masses, on the other hand, gave the opportunity to compare samples. We can simultaneously detect several polymers in a GCMS run that is quite quick. It's roughly about 2 hours, excluding the data evaluation that takes a long time as well. But we get ideas about geospatial temporal data comparison and can compare really data from completely different locations with respect to the mass, because any appearance is excluded in pyrolytical methods or thermoanalytical methods. We already see the principles, so I just go very quickly through it. Example is polyethylene. Here you see the equipment. We are using a microfinance pyrolyzer and just a single stage nominal resolution mass spectrometer. The sample is put in the pyrolysis cup, and from polypropylene we receive the pyrogram, and we get a lot of decomposition products, where 2 of those are quite indicative and used for identification. And we can change that to another polymer, here polyethylene terephthalate, which can be analyzed in different ways. We are using TMAH, tetramethyl ammonium hydroxide, which is a pyrolytic derivatization process, which on one hand cleave ester and ether bonds, and on the other hand form their methylated derivatives that improve their sensitivity, that reduce their polarity, and therefore it improves also the chromatographic behavior. And when you analyze the compounds, you get the characteristic mass spectra. From these characteristic mass spectra, one can derive via the software the extracted ion chromatograms, and with standards of different concentrations, you can generate a calibration curve, and with integration of these characteristic signals, you can identify simultaneously different polymers out of a very complex environmental sample, even if it's processed. We will see that several times, that even all these processing steps, yes, Follertson already shown the total ion chromatogram of these environmental samples still remains quite complicated. So here are all those characteristic fragment or decomposition products which we are using to identify different polymers. Here we see the traditional polymers that are 10 we analyze frequently, and the black or the dark blue frames show those polymers which are influenced by the thermochemolysis and give, for that reason, maybe some different fragments, as you have already shown in the other presentations. We also include tire wear particles in our portfolio that enable us even to differentiate between car tire wear and truck tire wear input. Okay, so we have seen the characteristic backbones that are detected to identify polymers, and that works pretty well if we have one distinct polymer and then thermoanalytical methods, not only pyrolysis GCMS, all thermoanalytical methods are able to identify distinct polymers. But in a complex environmental sample, it is not the case at all. As Ichi-san already mentioned, we have a lot of different polymer types that have the same backbones, and in a complex mixture, distinct characterization and identification is not possible any longer. So, for example, looking at the PE backbone of alkadienes, which are ideally used, and because we have this long unique polymer, we have a lot of different alkadienes that have to, or that are usually identified and used for quantification. And if we look at that, we have the same pattern observed for pure polyethylene, but also for ethylene vinyl acetate or for the ethylene polypropylene diene rubber. And the same holds true for the rubber and the polypropylene backbone or mochi, which is already or also included in this polymer. So all these polymers are detected as PE, or here for polypropylene. And another example is for the polystyrene backbone. Even if we take the very indicative trimer as an indicator compound, acrylonitrile butadiene styrene rubber or styrene acrylonitrile copolymers have the same signature as pure polystyrene. And looking for varnishes, here example an epoxy varnish and polycarbonate, which base both on biphenyl as one indicative molecule in the polymer net, even disregarding if with derivatization or without derivatization, we get also a signature for both polymers. So for conclude this statement, we look at all those backbones we identified and see that a lot of polymers are leading to those specific backbones in general. And looking at environmental samples, all these polymers can occur simultaneously. So nobody can really say we have only PE here or PS or whatever. So here a high necessity is demanded to define polymer clusters that we are talking about. What does it mean for identification? The polymer cluster now is defined, but for mass determination, we still use a pure polymer, which is very well defined, and we can do sophisticated calibration and quantification with it. But for giving results for the respective polymers, we definitely have to speak about polymer clusters for a given sample and for further data comparison. And these clusters should be continuously and critically questioned and also update as soon as other new compounds have to be included for a reliable data presentation. Handling of standards is quite different and is highly dependent on the lab facilities and also on the polymer properties. So we can have or handle solid polymers with direct weighing with, for example, an ultra microbalance, which is limited here. We have 0.1 microgram as the smallest unit, at least, to read. There are some polymers which are solvable, and that's the dream of every analytical person, because then we have the high, good opportunity to make dilution series and go very down with our calibration curves. And a third opportunity is a mechanically neutral diluting, using a neutral matrix to dilute standards and get then defined polymer standards, which enables also the use of an analytical balance. The optional derivatization I've already mentioned that we are using, and here it's just an example for the PET and the improvement in detection sensitivity, because if you not derivatize PET, you end up with a lot of decomposition products of different polarities, of bad chromatography as well. And with derivatization, you end up with almost one signal that enhances the sensitivity enormously. And last not least, something we recommend as well is to use an internal standardization. Why internal standardization? We have very complex pyrolytic processes, and during a sequence, a lot of things might also accumulate in the pyrolytic system. Here you see some very worse samples of sediments and some nicely samples which we are analyzing. We are coming to the cleanup process later. This cleanup process ends up on a 20 millimeter glass fiber filter, which then can be folded and put directly into the pyrolysis cup. This filter, as you can easily see, still have residual organic matrix. It has still residual inorganic matrix. We have in our system residual non-volatile pyrolysis products, and we have also frequently active surfaces inside the pyrolyzer or the cup. So we observe a lot of complex intercompound and surface interactions, which are highly discussed now in the community, that lead to signal interferences and also signal interferences to our indicator signals. So the first step, the first pragmatic step, is to mimic the conditions, how standards are measured and how samples are measured, most ideally to get comparable data. And the next point is to use an internal standard for the pyrolysis process. We have very good experiences with at least partly aromatic internal standards, like here our dodecyl octaanhydroanthracene, or like deuterated polystyrene. And what we observe are then, or what we hope with this internal standard, is a compensation of any interactions, and the assumption that this internal standard interacts with all these surfaces and compounds as our indicator ion itself, to compensate these effects, because now the standardization or the calibration is not performed as a function of area to mass of the distinct polymer, but as area of the indicator ion versus the internal standard. And what you directly see, that usually the linearity of the polymer calibration improves a lot. And actually, what we have found out for sediment analysis, for example, we measure these calibration standards with each sample sequence, and measuring PET, for example, here standard in a sediment sequence, and looking for the area of the respective standard data leads to a complete uninterpretable calibration curve. But then use the internal standard. This at least enable at all the quantification, because now we get a calibration curve and are able to analyze our samples. And a very nice point of internal standardization as well is that it enables even a retrospective analysis of already measured data for additional polymers which might come into perspective later. And because there is a measure in the data file, there is a direct opportunity to, yes, retrospectively look for other polymers as well. Now some examples for calibration curves for different background conditions. So here we see polyethylene and polypropylene, which are really hard to solve. And what I would like to point out is that calibration can change very quickly and very often just with respect of the state of the instrumentation. So you can also get a very beautiful polypropylene calibration curve. So these curves are just taken out of routinely measurements. And usually what we observe is, because we take 10 of the alkydiene signals of polyethylene and take the mean of all of them, we usually get a very good linearity and a very nice calibration curve. But the same holds true for polypropylene, where usually only one signal is used. The use of solvable polymers, here shown for PET, and look at the mass scale now, shows very nicely that we can then, with solved polymers, really go towards the defined detection limit of our instrument. And for this determination of detection limits and quantification limits, two methods are common. One is only taking the signal-to-noise ratio. We will show that later. And there you say the detection limit usually is a signal-to-noise ratio of a data point that have a signal at least that is 3 times higher. And for quantification, it has to be 10 times higher. You can use also a calibration curve-based method, which includes also analytical variations, which are also there. And usually those calculated measures are a little bit higher. So for example, here, use the calibration method. The limit of detection is just 60 nanogram in this example, looking for the signal-to-noise ratio. And keep in mind that 3 is usually the detection limit. We get at least even for 1 nanogram trimer. a detection limit or a signal-to-noise ratio that's even 6. And going to the monomer, which is not used because it's too much disturbed by other organic compounds, you can go even lower because the signal is higher. So all in all, instrumentation, preparation variabilities, background, contamination state of the instrument at least is the most important factor how good limits of quantification and detection are. Here is the summary just for signal-to-noise related data in microgram absolute, and you see we have different polymers with different detection limits and quantification limits, and these are data just from the common and nominal resolved system we use. But these data really underline the high sensitivity and analytical potential that pyrolysis GCMS have for mass-related trace analysis for micro and nanoplastics. There are a lot of more and more increasing methods that could enhance the sensitivity, such are measure options with respect to, for example, the split dilution of the system, different measure modes like SIM or in MS techniques, SRM modes, and of course, ultra high resolution systems which highly are able to improve all these data I shown. Coming now to some environmental samples, and that is also done, so or also already said, so I just go quickly through it. We have a very low microplastic content accompanied with high organic and high inorganic matrix load, and we have definitely in most of the cases to do or to perform an adequate microplastic pre-concentration to really get measurable and reduced amounts at least. So this matrix should be effectively removed on one hand, but should on the other hand not affect polymer types. And for pyrolysis GCMS, the very small sample cup we are using is quite the biggest bottleneck. So if you think about a kilogram sediment to go in this little cup, and usually we prepare a whole kilogram and really put everything then back into this cup, it is quite, a challenge. So all these techniques are already named by Jens Follertsen, so I just repeat that to keep them in mind, and you have a lot of different ways how to prepare an environmental sample, and hoping of a unique protocol is impossible. Usually you use even a succession of different methods, and all those methods are like building blocks, and you adapt your method to each sample individually. So we use sieve cascades, we use density separation, and density of 1.6 with sodium bromide is usually sufficient. We use also different separators. We use enzymatically approaches. We use Fenton's reagents. And as you see with all these pointers, we mix those processes depending on the sample. In the end, we concentrate our samples on anodisk filters if we measure them in a sequence with FTIR measurements, or on glass fiber filters, and then put them in our cups for measuring with pyrolysis GCMS. Now, some samples we analyze, for example, sea salt or marine salt samples. Here, a fleur de sel sample from Greece. And even though it's salt, it's just solved and density separated because it still contains a lot of sand. You see that the remaining chromatogram and organic matrix is still present because a lot of salt insects are also present in these salts. you see a nicely resolved, or you see nicely resolved ion chromatograms. And I have forgot to point that out. The most important, but we will see that later as well, are the procedural blanks during preparation to give you an idea about any potential secondary contamination. And this is shown here, that we always proceed a procedural blank. Here it's also shown to look on the traces if there is any additional signal of a respective polymer. So the resolution is quite nice here, as an example only for these selected polymers. If you do replicates, you see the repeatability of a natural sample is changing because you have particles, and you have only small amounts. So it is not a good way to homogenize the sample, and also to mill the sample might be a high or have a high danger of secondary contamination. So usually we take the sample as it is, and particles are different distributed in a sample. So you see this variability as a mirror of natural distribution of particles as well. Overall, we have a concentration in these salt samples in a ppb range. And the great thing of mass-dependent analysis is that you now can compare different geographical sites with respect to their polymer composition. And what you are seeing is that in case of these salt samples, the main polymers, the dominating polymers, highly reflect the plastic packaging demand. But you also see differences, for example, for the Mediterranean salts and the Atlantic salts. So you can discuss this on a geospatial basis. All in all, the fleur de sel have a higher microplastic content compared to the conventional sea salts due of the harvesting process and the harvesting process. I don't want to go into detail here. Another sample is the microplastic distribution in marine waters of the North Sea in the German Bight. If nobody is, or anybody is not familiar with the location, it's just given here. And what we see is that for looking at the cluster of PE, PP, and PET, we have very locally accumulation more close to the coastline. And here the most plausible plastic source would be, or is assumed to be, packaging related. Looking for the clusters of PVC, PMMA, and polycarbonate, we see a completely different pattern that is even more concentrated outside or far away from the coastline. And here might a relation to ship traffic is the case. And when we overlay the patterns or our results with cargo shipping routes of the same years where the samples were taken, we observe a quite high correlation between high levels and here, for example, and the transacts where these samples were taken. And this makes us make the hypothesis that the potential source for these high plastic concentrations are not usually packaging material, wasted material, but ship paints. And here is in particular polymer-based binders, and we call that the skip marks of ships. And if you calculate now, relying on our cluster definition, the impact of the ship paints compared to packaging-related plastics in these samples, at least, you end up with a relation of 80 to 20. That means that ships are a real high source for microplastic impact, at least in the marine environment. Another example is the comparison of tire wear particles and traditional microplastics, excluding here the tire wear particles in road dust and environmental samples. And what you see here is that, as one would expect in road dust, tire wear particles are highly present, but much higher in much higher levels than the traditional microplastics. Looking into sediments, the opposite is true, and just depending if it's river water or river sediment or marine sediment, even there the traditional microplastics becoming much higher. And looking at the marine salts, you see different levels. That highly depends on the areas and the frame conditions, how the samples were harvested, as also seen in the composition, which is given here more in detail. Overall, we can see that the closer the traffic source is, the higher the tire wear particle content is, and the far distance transport potential of tire wear particles seem to be highly restricted compared to traditional microplastics. The last example is a retrospective analysis of blue mussels, which was done in a cooperation with the Environmental Specific Bank of Germany, where we get samples that span a period of at least 30 years and were sampled each year to get an impact on insight into the microplastic composition over time, and also the specific composition of the single years, which gives a broad overview of different sources, etc., which will be published soon, and where we observed here microplastics, at least in ppm range. So overall, we can confirm that microplastics are ubiquitous and find them at least in ppb up to ppm range, in ocean water, even in ppt range, so in quite small ranges, while as closer as we come to higher influenced areas or influenced sources, or like wastewater treatment plants, the concentration is definitely rising. Road dust is in permeable range, so that is quite high. So coming to the last point I would like to point out is the contamination risk. And this is something one should keep in mind, in particular with the nano question. So it's not only the sensitivity of the instrument which is interesting or important, but also how we prepare the samples and how are the overall frame conditions. So it is highly recommended to do field blanks for all sampling process, like the used equipment, the used chemicals, and also the used storage. But lab is another part, and I will show some examples later, where you use different chemicals, solvents, equipments, etc. You have different degrees of protection of your lab. You have a different air exchange. You have different lab traffic. If it is the question, if you have a remote lab or if a lot of people going into this lab to take other gear. And you at least have also your instrumentation, the measurement environment, etc. So you definitely need a lab blank as well. In our lab, we use a field blank as a real separate sample to discuss how the potential of contamination is during sampling, while we use the lab blank usually for data correction. It is very, very difficult to give an insight on contamination, on secondary contamination in the lab, because it is highly dependent from the respective handling procedure and the general and actual conditions in the lab. So what I have done is just completely independent of wherever the blanks were coming from, give an idea about over 40 lab blanks, which are the main contaminant plastic types we see. And we very often find PMMA that is partly restricted to our gear. We also find PP, often related to gear as well. And the same holds true for PVC. We also find a PET, often related to fibers, which is most plausible and already mentioned in an earlier talk. So what we are doing is a data correction from our lab, or with our lab blank, and we subtract the detected areas from the areas measured from the sample. And if you look here you have a standard of 1.1 microgram PVC, and you see we do at least replicates of blanks in one sequence, because we have particles, we have different influences values, and to take then the mean. And you see it is always quite low. Sometimes they are below quantification limits. Sometimes they are in the area of 1 microgram. So it really depends on the complete handling. But if you subtract them, you can you make sure that the reliability of your data is increased. Giving some samples, you see here a sampling gear effect, and here polypropylene, because a polypropylene liner was used in this sample procedure. And what you're seeing is a sample itself, the onboard procedural blank with a definite polypropylene signal, the lab blank with almost no signal. And here you have, just to compare the order of magnitude, a polypropylene standard. And what can happen after you have then, or we have subtracted the lab blank from the sample, that you end up with procedural blanks here in the sample profile that are in almost the same category than the sample themselves. And that have usually the decision as consequence to exclude this specific polymer from any further discussion. On the other hand, here for polyethylene terephthalate, no blanks were visible, so that is a nicely interpretable sample set. Going to another example, we have prepared filtrated artificial seawater for a subsequent experiment, and to be sure that no plastic is in it, but we have just because we are keen on knowledge how much contamination might be in the sample, we filtered or measured the filter, and we get an extraordinary value for PET. Here is a little dirty system, so that is a typical effect of tailing if the system runs dirty, but only for getting an idea about the dimension. We get an enormous peak, and if this filtration is performed in a clean room here of the inorganic group in our institute, then it is completely gone. And you see it also here on the filter, that mainly polyethylene terephthalate fibers from lab environment are the reason. We can talk for a very long time, or a long time, over blanks. I think they are really important. That is the last example given for PMMA, and for two sites. On one hand, the filtration units. So we usually use a PMMA filtration unit and have a normal blank with this. But if we change, and we have done that now, to stainless steel filtration units, then you can lower this contamination. But what is shown here, even the TMAH reagent and also solvents can contain traces of polymers. So in this case, the batch has a distinct PMMA residue, and it is very small. So you see here the 1 microgram standard, and the signal is much higher. But at least there is a distinct signal that has to be kept in mind. So to come to a conclusion, the procedural blanks field and lab are the most important things to make and to have knowledge about these blanks to make any data reliable, because you have to demonstrate that the measured data are not or could not be traced back to the blanks and are really reliable data for your samples. So what you have to do is to use at first step representative sample sizes to compensate inhomogeneities from your particulate matter and your different polymer types as well. And usually your content should be in the comfort zone of your calibration. So you shouldn't handle or work always at the lowest end or even below your lowest calibration point, because then you really run into problems. And the concentration of your samples should be clearly above the blanks to be sure that you have good data. So I have already mentioned that. I don't have to repeat that all the time. Lab and procedure blanks are necessary. And of course, we shouldn't, or we have to just mention that you should avoid any synthetic gear in the lab, choose an appropriate environment, test, pre-filtrate, recrystallize, and wash all your chemicals and solvents to get as low as blanks as possible, and then always perform also blanks to test these processes. So, coming to a summary, pyrolysis GCMS have a very high potential of sensitive detection of microplastics and nanoplastics. And I think we have not reached the end regarding the sensitivity of the methods, because we have a lot of options to improve this. But we also see everywhere, ubiquitous in all lab chemicals, etc., microplastic, nanoplastic contents. So the importance of the blanks becomes really relevant. But first of all, to be in line, the polymer backbones need a cluster definition. So we have to be sure, if we would like to compare data between studies, we are talking about the same masses. Then we definitely have this secondary contamination problem and the ubiquity of polymers. So the blanks are most crucial and as important as the samples themselves. And this is in particular relevant if we are going or looking for very small particles, because they have also higher interaction potentials. Matrix reduction, we have a lot of losses there as well. And the preprocessing procedures and the blanks becoming more relevant. So now I have finished. Sorry for the long talk. I would like to thank my whole team at University of Oldenburg, all the students, all the funders, and I'm looking very forward to any questions. Thank you.
Thank you very much, Dr. Barber. Excellent presentation. Actually, we have quite a number of questions in the question box. Maybe I take 2 questions, and remaining questions we put you in you're in the Q&A panel discussion also. We can discuss in there as well. Yeah. Okay. Let me read one of the first question. How often must the pyrolysis GCMS be calibrated with the different polymers, given the issues that not all polymers can be soluble?
So usually we have are running calibration with all sequences we are running in the pyrolysis GCMS. So the calibration is an inherent part of each measurement, and not only one calibration point, several calibration points to have a good calibration statistic. And we weight all single polymers in one standard cup. So this is a long procedure. So if they are soluble, it's great. And for the other things, we use students to weigh them really manually, picking small particles. And I think this is one of the most challenging and time-consuming parts. So there are some promising improvements with respect to calibration performance and performing calibrations, and I'm looking very forward to these. So these dilution things, and maybe somebody then sell standards, prepared standards. So this is the wish of everybody working with microplastic analysis. But very important is not to do a calibration and just leave it and then analyze samples, but always include calibration and use internal standardization, because sometimes calibration can be compared between sequences and it looks very good. But if you have a very dirty sample sequence, the complete calibration might break down and you have to do maintenance of the whole system.
Thank you. There's one more question here. When measure using the pyrolysis GCMS, is there a probability to obtain inconsistency fragment? How can we define the characteristic of every mass fragment as a polymer identification?
So you have to look definitely for interferences also with natural material. For example, in the first presentation today, the styrene monomer, for example, is completely unusable because it's generated from chitin of the poly. And you have a lot of others where you can be sure. So the first point is really to pre-clean your sample to get rid of all as much material, organic material as possible. And then you have really to go into your sample and check if you have cellulose, if there are interferences, etc. And that is something we find out that was a good decision from ours to derivatize samples, also make interactions smaller and secondary reactions smaller because the polarity is decreased. But you have to be always aware that as the more organic contamination or metrics you have in your sample, the higher the risk of additionally interferences is. And looking for at least longer parts of a polymer, so trimers or pentamers, with respect of choosing them as indicator fragments is also a very good choice, and not to go to monomers or to go to two common pyrolysis products, because then the interferences won't end.
Okay. Thank you very much, Dr. Barbara. Excellent presentation. Thank you very much once again. There's more questions, more issues will be discussed in the panel discussion at the end of the day today. Yeah. Thank you very much once again. Okay. Can you